Okay, this is chapter 21. No, I'm sorry, chapter 20, induced voltages and inductance. Um, so let's get started. In 1819, Hans Christian Ørsted discovered that an electric current exerted a force on a magnetic compass. His finding was the first evidence of a link between electricity and magnetism. Because nature is often symmetric, the discovery that electric currents produce magnetic fields led scientists to suspect that magnetic fields could produce electric currents. Experiments conducted by Michael Faraday in England and independently by Joseph Henry in the United States in 1831 showed that a changing magnetic field could induce an electric current in a circuit. Now, the key word there is changing, a changing magnetic field. The results of these experiments led to a basic and important law known as Faraday's law. In this topic, we discuss Faraday's law and several practical applications, one of which is the production of electrical energy in power plants throughout the world. Okay, take a look at the figure. The apparatus consists of a coil connected to a switch and a battery. We call this coil the primary coil and the corresponding circuit the primary circuit. The coil is wrapped around an iron ring to intensify the magnetic field produced by the current in the coil. A secondary coil at the right is wrapped around the iron ring and is connected to an ammeter. The corresponding circuit is called the secondary circuit. It's important to notice that there is no battery in the secondary circuit. There's also no physical wire connection between the primary and the secondary. It's only the iron ring that connects the two of them, and it's not conductive. At first glance, you might guess that no current would ever be detected in the secondary circuit. When the switch in the primary circuit is suddenly closed, something amazing happens. The ammeter measures a current in the secondary circuit and then returns to zero. When the switch is opened again, the ammeter reads a current in the opposite direction and again returns to zero. Finally, whenever there is a steady current in the primary circuit, the ammeter reads zero. From such observations, Michael Faraday concluded that an electric current could be produced by a changing magnetic field. The current produced in the secondary circuit occurs for only an instant, while the magnetic field through the secondary coil is changing. In effect, the secondary circuit behaves as though a source of EMF were connected to it for a short time. We say that an induced EMF is produced by the secondary circuit by the changing magnetic field. Okay. The physical quantity associated with magnetism that creates an electric field is a changing magnetic flux. We define magnetic flux the same way as electric flux. It is proportional to the strength of the magnetic field passing through the plane of a loop of wire and the area of the loop. The magnetic flux through a loop of wire with area A is defined by the equation shown here, where B perpendicular is the component of a uniform magnetic field perpendicular to the plane of the loop, as in the figure on the left. And theta is the angle between B and the normal to the plane of the loop. So it's only the perpendicular component of the B field. I think it's better seen in the figure on the right. And that's a cosine theta term. Note that there are always two directions normal to a given plane surface. In the figures here, for example, that direction could be chosen to the right, resulting in a positive flux. The normal direction could also be chosen to point to the left, which would result in a negative flux of the same magnitude. The choice of normal direction is called the orientation of the surface. Once chosen in a given problem, the normal direction remains fixed. A good default is to choose the normal direction so that the initial angle between the magnetic field and the normal direction is less than 90 degrees. From our equation, you can see that the magnetic flux is the magnitude of the part of B that is perpendicular to the plane of the loop times the area of the loop. The figure on the right is an edge view of the loop and the magnetic field lines through the loop. Okay, when the field is perpendicular to the plane of the loop, as in the figure on the left, theta equals 0, and the magnetic flux has a maximum value. In other words, all of the green lines are going through the plane of the loop. So the magnetic flux at that point through the loop is a maximum and equal to theta equal to B times A. In B, when the field lines are parallel to the plane of the loop, the magnetic flux through the loop is 0. In other words, they're just going beside it. They're not going through the loop. When the field is perpendicular to the plane of the loop, as in the figure on the left, theta equals 0, and the magnetic flux has a maximum value. I think I just read that. When the plane of the loop is parallel to B, as in the figure on the right, theta equals 90, and the flux is 0. So it must be important if I repeated it. The flux can also be negative. For example, when theta equals 180 degrees, the flux is equal to minus BA. In the figures, we represent the field strength by the number of lines per unit area. That means the value of the magnetic flux is proportional to the total number of lines passing through the loop. Of course, the lines are imaginary. It's just a representation of the intensity of the magnetic field. You can see that most lines pass through the loop when its plane is perpendicular to the field. When the plane is perpendicular to the field, as in the left-hand figure, so the flux has its maximum value at that time. As you can see in the right-hand figure, no lines pass through the loop when its plane is parallel to the field. So in that case, the flux is 0. So think about the normal. The normal is the little vector that's coming off the, I don't know if you can see the cursor. The normal in this, in A, would be a vector pointing to the right. And it's in line with the magnetic field. So theta equals 0. And so BA cosine theta, BA cosine 0 degrees is cosine of 0 degrees equals 1, so it's just BA. And here in B, the normal to the loop would be in either the up direction or the down direction, depending on which you choose. But whether it's 90 or 270, the cosine of either of those is 0, and so the flux is 0. Okay, this ends the introductory section. The next section we will discuss is section 20.2, Faraday's law of induction and Lenz's law.